Hey, what's up, chemistry people? It is Mr. Boylan, and we are going to do a quick free response practice problem here to sort of put some of those notes that we just took on acid-base equilibrium into perspective. If you take a look at the free response practice question that you're provided with in your notes, the very first thing that we are provided with is an equation. And that equation also has a Kb value, 1.80 times 10 to the negative 5. So as I look at this equation and think about some of the notes that I just took, I recognize that the ammonia molecule here is acting as a base. In other words, it's going to act as a proton acceptor. So this is going to be my base, and its conjugate acid is going to be the ammonium ion. Similarly, we've got water, which is acting as an acid or a proton donor, and its conjugate base is going to be the hydroxide ion. The Kb value of 1.80 times 10 to the negative 5 implies that the base, ammonia, is a weak base. As we look at this solution, we're going to have mostly reactants in that solution. So that said, let's take a look at the first part of this question. It says, write the equilibrium constant expression for the reaction represented above. Remember that your equilibrium constant expression, in this case, will be expressed as Kb because we're talking about a base, is related as the concentration of the products over the concentration of the reactants raised to their stoichiometric coefficients. And so if we look at this, our products are going to be the concentration of the ammonia ion times the concentration of the hydroxide ion over the concentration of ammonia. Okay, and you get 1 point for coming up with this correct expression here. Always a good idea to box in your answers so that your AP graders know what exactly your final answer is. Part A, complete. Okay, let's look now at part B. It says, calculate the pH of a 0.150 molar solution of NH3. Now, to tackle this problem, if you've forgotten what the formula for pH is, lucky for you, it's on your formula chart. If we take a look at some of the formulas provided to us underneath the equilibrium section, we will find a formula for pH, which is equal to the negative log of the hydrogen ion concentration. So I'm just going to write that here to remind me that I need to solve for pH, and the way to do that is to figure out what the hydrogen ion concentration is, so I can take the negative log of that value. Now, as I look at my problem, I don't have a hydrogen ion concentration given to me directly in this problem. So I have to think about some of the other ways that I can derive the hydrogen ion concentration from the information that I'm given. You should recognize that you are also provided with this relationship between pH and pOH. And so additionally, I have this relationship pH plus pOH is equal to 14.00. So to sort of wrap your mind around what we need to do to solve for this problem, we need to figure out what the pOH is. And so then the question becomes, well, how do I figure out what the pOH is? Once again, as you take a look at your formula chart, we've got an equation for pOH, very similar to the formula for pH, which is equal to the negative log of the hydroxide ion concentration. So once again, I'm putting another formula there, pOH is equal to the negative log of hydroxide ion concentration. So to sort of wrap your mind around what we need to do to solve for this problem, ultimately we're trying to get the pH. That's what this question is asking us. But the problem is we're working with a base, and our equilibrium constant expression isn't going to give us concentrations of hydrogen ion, it's going to give us concentrations of hydroxide ion. So we need to recognize the relationship that exists between pH and pOH, and then in order to plug it into this equation and ultimately determine what the pH is, we need to figure out what the hydroxide ion concentration is. All right, so to help make this a little more clear, the very first thing that we're going to do is solve for hydroxide ion concentration so that I can figure out what the pOH is. And I'm going to work in that same color pen here so you can sort of see the process to solve that. I'm going to rewrite this equation, NH3 plus H2O, get my equilibrium arrows here, to produce the ammonium ion and the hydroxide ion. Now, to figure out what the hydroxide ion concentration is at equilibrium, we're going to set up an ice table. My initial concentration of the ammonium ion is 0.150 molar. I'm not going to include water in this ice table at all because it's a liquid and it won't be included in our equilibrium constant expression. My initial concentrations of the ammonium ion and the hydroxide ion are both 0 initially. The change is going to be a decrease in X here and an increase in X for both of those ions. The relationship is just X in each case because the ratio in the balanced equation is 1 to 1 to 1. So my equilibrium concentration for ammonia is going to be 0.150 minus X. And these are just going to be X and X. Now in this example, we can neglect the change in X for our ammonia concentration. And the reason why we can do that, and the general rule of thumb to let you know when you can just neglect X, is to think about what the initial concentration was and compare that to your K value. If the concentration is 1,000 times larger than your K value, then the change is going to be small enough that it's not going to have a huge effect on the pH of the solution. So what this means then is our equilibrium concentrations for the ammonia ion are 0.150. For the ammonium ion is X, and the hydroxide ion is X. Now if we plug that into our equilibrium constant expression that we did in part A, we end up with X times X over 0.150. And we're given the value for Kb in the problem to be 1.80 times 10 to the negative 5. I'm going to do a quick calculation using my calculator here. 1.80 times 10 to the negative 5 times 0.150. Essentially, I'm trying to isolate my variable X here. I end up with 2.7 times 10 to the negative 6 is equal to X squared. So to determine what X is, and therefore the concentration of my hydroxide ion, I simply need to take the square root of this value. So second square root of that answer tells me that the hydroxide ion concentration and the ammonium ion concentration is going to have a concentration of 1.64 times 10 to the negative 3 molar. Okay, now all of this work, and I haven't even solved for the pH of the solution yet. All I've done is determine what the hydroxide ion concentration is for this solution. And to figure out what the pOH is equal to the negative log of the hydroxide ion concentration. And we just determined the hydroxide ion concentration to be 1.64 times 10 to the negative 3 molar. Therefore, the pOH of this solution, I need my calculator, negative log 1.64 second E negative 3. My pOH is going to be 2.785. Remember the rule about significant figures when you're doing logarithms. The total number of sig figs here are 3, and so that's the number of significant digits that I'll have after my decimal. So 2.785 is my pOH value. Okay, now remember we're trying to figure out what the pH of this solution is, not the pOH. And so as we look at this equation here, pH plus pOH is equal to 14. And so if we work to solve this problem, again, pH plus pOH is equal to 14. I'm looking for the pH. The pOH we just determined to be 2.785 equal to 14. I plug that into my calculator, 14 minus 2.785. And we end up with a pH that is equal to 11.215. Again, I'm going to box that final answer for that part of the question in. It's really important to make sure you're very clear, not only in showing your work, but also showing what your final answer is. As I look at this, this is worth 2 points. You get 1 point for showing how you determine the hydroxide ion concentration, and you can't just throw the number down. You have to show mathematically how you determine what the hydroxide ion concentration is. And then a second point is for the calculation and correct determination of the pH. Again, you can't just throw down 11.215 and expect your AP grader to give you full credit. So make sure that you show your work in both cases in order to get full credit. Okay, as we take a look at part C, we're asked to determine the percent ionization of the weak base. Now, unfortunately, there isn't a formula on the formula chart to help you remember percent ionization. It's something you have to memorize. However, it's pretty straightforward like any other percentage. It's just the part over the whole. In this case, we're talking about the part that's dissociated, or what is my concentration of hydroxide ion over the original concentration of the base. Now, recognize if we were asked to do this for an acid, it would be the hydrogen ion concentration over the original concentration of the acid times 100. That will give us our percent ionization. Now, in this question, the hydroxide ion concentration comes from part B, which we determined to be 1.64 times 10 to the negative 3. The initial concentration of the base was also provided to us earlier in the problem to be 0.150 molar. A quick division and then multiplication by 100, which means the percent ionization, not very much, which we would expect for a weak base, to be 1.09%. As always, you want to make sure that you box that answer in to very clearly show your AP graders what your final answer is. It's really important to also show them your work. You get 0 points for simply writing 1.09%. All right, if we take a look at part D, then it says calculate the hydronium ion concentration in the above solution. Be sure to include units with your answer. Now, this is only 1 point, so it's very obvious that if I don't get the right units here, as in many cases, you're not going to get the points, even if you do the work correctly. Now, for this problem, however, we do have a formula provided to us on the formula chart that will help us solve this problem. It's this one right here. Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. And if we rewrite that here on our paper, we end up with Kw equals hydrogen ion concentration times hydroxide ion concentration. Recognize that hydrogen ion and hydronium ion are interchangeable here. The Kw at 25 degrees Celsius is 1.00 times 10 to the negative 14. Hydrogen ion concentration, we don't know. That's what we're looking for. Hydroxide ion concentration we're provided with in part B of this problem, or we solved for, to be 1.64 times 10 to the negative 3. So X equals, which is our hydronium ion concentration, which remember is the same as hydrogen ion concentration. 6.10 times 10 to the negative 12. Always a good idea to box your final answer in. Again, simply putting this answer down will get you 0 points. Also recognize that if I walked away from this right now, which I almost did, I would still get 0 points because I forgot my units. My units here are a concentration. We're talking about molarity. So don't forget those units. I did all of my work. I would have gotten 0 points had I not gone back to include my units. So watch out for units. A, B, C, D, done.